Okay, well, hi everyone. For those of you who don't know me, my name is Nic Jelinski. I'm an assistant professor in the Department of Soil, Water, and Climate. And on behalf of Al's entire committee, I'd like to thank you for joining us today. I'll also be moderating the questions at the end. And as Al's primary advisor, I have the great honor of introducing him. I was thinking about this for a long time. This is not an easy task because I think I could probably give a 50-minute seminar just on Al. And any of you who have had the pleasure of interacting with Al over the past years know what an amazing and inspiring person he is. Al completed his bachelor's in soil science at the National University of Zaire, now Democratic Republic of Congo, in 1978, followed by a master's in ag econ at Ohio State University in 1992. I first met Al in 2014, and we immediately found that we shared an inexplicable bond. It's been this bond and Al's relentless vision and optimism that has driven both him and me through his PhD program. Working with him has truly been one of the greatest honors of my life. During his PhD journey, Al has persevered through tremendous physical hardships and personal tragedies. Al conducted his PhD research near his birthplace, as you will see. And so his work is both professional and deeply personal, a labor of both love and duty. Al is an eternal optimist whose light touches everyone he meets. The sheer breadth of his life experiences are stunning. He speaks 6 languages. English is actually his last. And in addition to his BS and MS, he holds 3 associate's degrees. Oftentimes when I've called Al to ask how he's doing, he says, well, still standing upside up. And I think we would all do well to greet every sunrise the way that Al greets them, with gratefulness, with passion, and with an insatiable drive and curiosity. I've been fortunate to share this journey with Al, and I'm honored to call him a friend, a brother, and a fellow pedologist. We have become family. Following the completion of his PhD, Al will be traveling to DRC to teach at the University of Notre Dame at Shumbe in Sankuru Province, DRC. And I look forward to the day I can sit in the back of his class and learn from him. As you'll see through his work, Al has truly become a global expert on the soils of central DRC. So thank you all very much for being here. And with that, Al, I will turn it over to you.
Thank you, Nic, very much for those very touchy words that go straight into my heart. Thank you. Hi, everybody. I'm gonna be getting ready here. Technology allows to start my talk. For technological reason, I think my face is not gonna be shown. It's gonna be cut off, so no more distraction on the screen. And from there on, I will be holding the spot. Thank you again. This can come down. We'll be there shortly. Okay. Good. I hope everybody sees those images on the screen. All right. Good. I'm going to be taking you to Central Africa, into the Democratic Republic of Congo, and more specifically in the province of Sankuru, to share with you some findings of my soil study in that province. I need to tell you right away that, as you heard, that I was born in that province. So this is kind of very personal. The topic of my study involves how climate and vegetation are impacting soil genesis, soil properties, and soil distribution. This study was conceived in the context of food security and the lack of soil information in DRC. As you can see, information really plays a critical role in land use planning and agronomic development. Congo, unfortunately, has been known to be one of the countries with the least data dense. The picture that you see in front of you right there in the red dot, that the globally known soil profiles around the globe. You see the United States, Western Union, and the DRC. You can believe your eyes when it's very dense that we have access to more information. And in the DRC, almost nothing. It's very, very fluid. And that really is a concern. Is a concern because the soil in Congo has been poorly characterized and poorly mapped. You see the next two pictures over there, Rwanda, Burundi, that's a very detailed soil map. And then on the top of that, you have a DRC, in central DRC, which is, it seems like one single theme, but those two pictures have the same scale. So really, soil information is pretty an issue in Congo. For me, Congo, especially central DRC, is ecologically and epidemiologically diverse. So it's very well mischaracterized over there. Soil data access to soil information also is very, very critical to boost local farming initiatives. The picture you see there, that's called shifting cultivation or slash and burn, that has been practiced in Congo for centuries. But right now, that system has been overwhelmed by demographic pressure that led to shortened fallows and resulting in very low yield. Am I still okay here? So for me, my personal approach is that agriculture has to remain local. That's the way it should be, because soil information from other places really not going to solve the agricultural problem in central Congo. So setting together a partnership with the local institution to build capacity is key. And that's one of the reasons I choose this project to be developed at home, where I know people know me, and we can connect, and I speak their language. In the same token, I managed to partner with the local university to conduct this research. So that being said, for the rest of my talk, I will be emphasizing three parts. Number one is how soil properties and the genesis vary with the climate and vegetation. That's section number one. Section number two, how stable have climatic and vegetative boundaries in Sankuru Province been for geological time. And three, we find out how in that environment, how phosphorus has been impacted. And then we'll end up with some general consideration about pedogenesis and agronomic implications. So in my introduction, I start with the area. We have a climate gradient. Climate gradient, as you can see where that triangle is located. Let me bring my cursor right there. Yeah, that's Sankuru right there. Okay, and that's the spot that we chose to do the research. It's about 250 kilometers long. We were so lucky to find that spot because within 250 kilometers, we were able to find 3 distinct climates going south from tropical savanna here all the way north to equatorial rainy forest. And that provided an opportunity really to see how climate gradient and vegetation gradient really impact soil properties. And as we go north, seasonality also changes with the increasing precipitation. And on the next picture, you see in red, that's where there is no break. It rains almost every single day. As we keep coming down, then the seasonality increases as the dry season takes on. Again, within the area, vegetation. You see here the 3 climate zone. Here, AW, that's a tropical savanna. Here, AM, that's the tropical monsoon. And AF, that's equatorial rainy forest. AF, AM, AW, that are the code done by Köppen system. That should be familiar. This is how it looks like in AM. That I gave you some pictures of the savanna in AM, AW, and AF. And the white spot there represent areas where we went to take samples with dog pets. But the problem with that is it was difficult to access those areas. As you can see, I used vehicles, I used motorcycles. I didn't use a bike, but I did walk. And both break down, you can see down here. And a very quick parenthesis here that I wanna make open, I would say, is that the vehicle that I used was my family, my young brother's vehicle. And himself is inside that vehicle right there as a driver. And next to the vehicle, that's my brother, who is number 5 in the family. The one in the car is number 4 in the family. And the young lady out there is number 6 of the family, and she was in charge of our kitchen. So this is very, very personal. Here we show you few pets, how we were digging them 2 by 2 by 2. And even while we were there, it was raining, so we had to do something to save the profile. We dug a 26 pit, and we described described the 130 horizons, and they took 429 samples. Now, after testing, in general, this is how it looks. Not pretty, I might say right away. It's a very sandy soil. pH very low, 4.4 on the average. Low CEC, 1.5. And the organic carbon on average, 0.9%. And in the colloidal fraction, you have a kaolinite, gypsum, and iron oxide that really make up that section. So it's a very, very, very depleted soil. And the sandy soil really is a huge challenge to food production. I selected a couple figures here to illustrate the interaction between those variables that I just mentioned, organic carbon and the CEC, organic carbon and the bulk density, how that interact. You can see right away that the regression is pretty sharp. That means a slim change of carbon has a quick repercussion on the CEC. It increases pretty sharp right away. And the same for organic carbon also. If it increases a little bit, the bulk density drops exponentially. That's simply because it's sandy. That's probably one of the advantages of having a soil sand. But no, I'm not gonna go that far too much. pH, the last figure here, and exchangeable aluminum, yeah, we are at 4, so we're really running risk of aluminum toxicity. How pH and phosphorus have been impacted by climate and vegetation. Savanna has appeared to, in our case, having higher pH than a forest. But in any case, climate had no effect, regardless of the climate. pH is always higher in a savanna. For phosphorus, gray phosphorus, savanna still have higher phosphorus than forest. That that difference there really depends on the climate zone, because you can see here down that at AW, it is savanna there, has the same level of almost the same level as the forest. Soil classification. We identified 5 different soil orders, Entisol in a AF, which is, let me bring my cursor, yeah, you can see it. Entisol there, we identified the spodosol, Ultisol, and Oxisol in AF. And this picture, I said there, in AF forest Oxisol, these pictures here shows the type of soil found in the AF zone. That forest, and this is savanna in the AF zone. For the first time, I might admit here, I realized that we can find savanna in the middle of equatorial forest. That has never crossed my mind before until I went down there. Inceptisols really were found mostly in the south here on the AM. I keep losing my cursor, yeah, okay. In AM and AW, that's where we found identified more of Inceptisol. Umbric epipedon was more about 87% of our described the profile was found in the south, yeah, in AM and AW. Ochric epipedon in AF, of course, 82% of was present in 82% of our profile in the AF. And We identified also some diagnostic horizon, candid and oxic. We saw also that there was the soil diversity that was mainly present in a equatorial forest, AF, and in soil order and the suborder. That's where we found much of diversity. We did use the Simpson diversity index to help quantify that soil diversity. And that index goes from 0 to 1. So if it's close to 1, the higher the index, the more diversified is the soil in that category. This is a very quick, just a 2-second here to show you that we have identified the spoiler soil in AF 2 degrees south of the equator. It's on my right there. And out here, the first image, it's very unique situation that I came across on the field. I decided to take a picture of it because that's the entire profile, 2 meter, dark as you see it. But believe me, it's not a histosol. So this is just a coloring, show how really infiltration is serious. I've never seen this before, this dark in the middle of in the tropical zone. Now I'm going to talk about the texture. I told you that it's about 90% sandy. Yeah, you heard me. 90% sandy. And that we have 46% fine sand. Very fine sand is 10%, medium sand 27%. So we have between very fine and fine, it's about 56% fine and very fine sand. That's a pretty light size. Coarse 4% and very coarse is a 10th of that. We put a picture here so that you can see. What I'm holding here is a blocky structure coming from the wall of the profile. And we cleaned that. And from there, we were able to identify all different sand, very fine, medium, coarse, and very coarse. The very coarse is just a couple of grain of quartz there. The amazing thing with the sand is that we try to see how it is distributed. And then running these figures, you can see that going from north to south, because it's changing with the latitude, 2.5 degree north, going south to 4.5 degrees south. We see that all coastal material decline going south. But every lighter grain size is increasing going south. So we think because the way it was very well sorted and the direction, the distribution with the latitude, we conclude that it has to be aeolian activity that probably resulted in this distribution. And that was definitely illustrated here. This is central Congo. And we thought that the sand was blown coming from north here down south in Sankuru. And what you see in blue, that's what is called a Kalahari group or mega Kalahari. it is a geological structure that went from south all the way in the central Congo, in the Congo River Basin. And because of the erosion that has taken place here, so the entire structure kind of lost some of its constituent, but still influencing the distribution of sand. To conclude this first chapter, first section, I would say, the soil is very, very weathered. Plenty of kaolinite, gypsum, and quartz. The pH is very, very low, and low CEC as well as base saturation. We notice also that the pH, of course, they grow with altitude, with the precipitation. The higher the precipitation, the more acidic it is. And under savanna, we identified umbric epipedon along with the under forest in the north, where we saw some eluviation, clay eluviation, and we identified some incipient or mature E horizon. Second section is about the environment, how the boundary between vegetation and the between savanna and forest, different climate zones have been shaped for some geological time. And I loved here, I brought here sketches published in 2017 by Hogg and the Svenning that kind of summarize what happened since late Pleistocene up to today, Anthropocene epoch. The forest and the savanna have been shrinking, expanding, shrinking, expanding up to today, following glacial and interglacial periods. And you can see also here that we still have some shrinking here. We have not gone back to the maximum expansion that we had 5,000 years ago. And wonder if this will ever come back as the climate evolves the way it is. To understand how that happened in that kind of paleo climate, we relied on the data related to carbon-13. And the carbon-13 is one of the stable carbon in the air, along with the carbon-12. They enters vegetation, they enter plant through stomata, and then reach plant tissue. When the plant dies, the tissue got into the soil, and then we go and take sample of that tissue. And then we're gonna measure the concentration of the carbon 13 in that sample. And from that, we will learn that the origin of that carbon. And from there, we will know that, okay, this came from forest or this came from grass. How that works? Always in a sample, there is carbon 13 and carbon 12. And they calculate the ratio in the sample. And then that ratio is compared to the ratio of carbon 13 and carbon 12 in the standard. So the ratio of those ratios gives us what we call delta 13, which is identified by some specific numbers. So delta 13, a value range from -24 or -22, depend, up to -32, when it's located in that interval, that means that the carbon comes from plant C3. And for the sake of this discussion, C3, very quickly, without going into detail, relates to trees. And if that ratio is located between -10 and -17, that means that the carbon came from grass. That's a C4. So after doing that, here what we got, extremely important result, very revealing. We have a vegetation. Actually, we put the result on the climate and the vegetation. But I prefer to talk about vegetation, but vegetation is much, much more revealing here. In yellow, that's a savanna. We combine here all three savannas. Savanna in equatorial rainy forest, savanna in a tropical monsoon, and savanna in tropical savanna. And the next is the forest. Very quickly about forest, you see forest start here at around about -30. And that is, we are completely within the zone of forest. And it comes down to -25. Remember, the range for forest is from -22 to -32. So we are right in the middle of, so no discussion there. What is there is just trees, or the carbon there came from trees. Where really we saw proof of shifting is here. You can see that the yellow one, it starts at around -12. -12, that means in the C4 zone, that's grass. And as we go down, at 50 centimeter, we are already at about a little bit more than -17. I'm checking -17 down here, and it smoothly comes down. We have to reach 100, about 100 centimeter, about a meter deep, to see that we are approaching the forest zone, the C3, because we are closer there to -20. So we are approaching the forest zone. And by the time we get to 2 meter deep, we are barely into the forest zone. So this area here, we have lost every trace of, not quite every, but we have lost a lot of trees, the carbon from the trees. The dark there, we see that's standard deviation. See? So in some time, it can go really there and it can come back here. Now, I'm gonna shift to the next one to really illustrate how dynamic is the vegetation turnover right in the spot of Sankuru. I splitted the three savanna. So the darker one, that the AM savanna, the yellow, the brown one, that's this one, okay, right there, yeah, that's tropical savanna. And the most important one is coming from this yellow one, is coming from the savanna inside the equatorial forest. And I wanna point that right away, that the from a tropical, from a equatorial rainy forest, this curve, the yellow one, it is start like everything else, like other curve right about minus 15, minus 13, somewhere there. And we come down to about closer to 50, less than 50. We're still in the grass zone. At that point, there is a plateau. It could not continue down. It kind of slide over here to already at before 50 centimeters. The presence of C3, a carbon, is already felt. So by the time we get to right here at 50, we are already here at closer to 20, to minus 20. When you compare that to other lines, they were still in a grass zone down here. Oh, just my cursor, yeah. Down here at more than 50, they're still in the grass zone, and that shows that at that zone, at that level, grass is still dominating. But for the savanna in the middle of a forest, really, C3 is still impacting. We got here at the minus 20 only at around 70 centimeters. So that shows that really C3 is there. That means forest just left, I would say so. So it shows how grass is encroaching into forest. And if we come all the way down, we have to reach about 70 there to come straight to minus, would say 23, somewhere there. Very quick remark here is that, sorry, what you see that a straight angle there is that for the first time we were taking samples pretty quick, normally sequentially, but when we got at the 2 meters, we were wondering what we would find deeper. So we sent samples again, and that sample was taken at a 3 meter deep. And when it came back, we found that it was still within the forest. So deeper we go, deeper we get into the territory of C3. That means trees. So that really shows how the grass has been invading what used to be invading forest. And that's really, to me, a revelation of what is taking place now in our transect. To conclude this, really it shows that the boundary between savanna and forest is very transient. And we saw also that in the climate, in the AF, still the dynamic of shifting is recent. It's like forest just left. I think that's what I would say right now for this a slide in terms of concluding this first part or the second section. We are now in the third part, which involves phosphorus. This is very, very, very important. Phosphorus, not only because of its physiological role in biomass, but also its its role, its importance, its connection with pedogenesis. Talking about the role of soil, the dynamic of phosphorus in the soil, we went back to visit Walker and Sayers, which are the scientists from New Zealand. In 1976, they published an article that they entitled the fate of phosphorus during pedogenesis. They use a conceptual model that you see there, which rely on it's a chrono sequence. So at the time zero, they looked at the apatite, the mineral that they contain phosphorus. And over time, that mineral was losing phosphorus, and phosphorus was being converted into occluded phosphorus, non-occluded phosphorus, and organic phosphorus. And as pedogenesis increases, the soil reaches the terminal steady state, where basically this is it, the end of the road. And they predicted that at that time, when that time came, after 130,000 years, there will be only organic pool and occluded pool. That's how they predicted it. Okay, so we said, okay, we in Sankuru, we are not at here at the beginning here. We are already with our weathered soil. We are at a terminal steady state. How phosphorus is behaving in that environment. That was the question we put. So the first thing we did, okay, we're gonna test the soil. We're gonna test the phosphorus. For that, we use the Hadley phosphorus extraction method. That is a very sequential extraction method where we have one single sample, and sequentially you use the different extractant, and each extractant comes with phosphorus that is identified as operational fraction. We identify it per the type of extractant used to take it out. That's where you see bicarbonate PI, bicarbonate PO, hydroxide PI, something like that. And doing that, there were a couple assumptions. Number one, we expected that the reactant will extract the soil P in a discrete chemical form. That's just our assumption. The reality may be completely different. And also increasing harshness of reagent associated with the increasing difficulty of P extraction by plant. That was our two assumptions. And at the end, I must say right now, before I forget, that this analysis about phosphorus was made in the laboratory of Professor Andrew, that I thank him and his team for the quality data that we received to do this analysis. Thank you. So after that, we got the extractable P. All those fractions were extracted, but from the sample, we still have some residual P remaining, of course. And for that, to find out about the residual P, they went in Andrew's lab, they measured total P using nitric acid and H2O2. And once that was determined, the difference between total P and extractable P gave us the occluded P. So we have now the whole structure of of phosphorus. After doing that, we also tested Bray P. Yeah, Bray, you can't escape that. That's a classic. So the result was what? At this figure, we have combined savanna and vegetation. And it came out that total P is very low in AW, somebody in a tropical savanna, and pretty high in a tropical monsoon and tropical equatorial forest. But the thing is that occluded P is very high in equatorial forest here, and very, very low in a tropical monsoon and tropical savanna. In the middle here, you see the presence of sodium hydroxide Pi and sodium hydroxide PO that kind of show remarkably there. Here, when we separate savanna from separate savanna and forest, there is another dramatic change. Total P is very high in savanna. And in forest, here, it's barely passing 100 grams per square meter, but this is in stock. And in savanna, it goes beyond 300. That's huge. And of course, AF here, we can see that occluded P is about 50% of a total phosphorus in AF forest, basically, because in our concept we had forest and savanna in a tropical monsoon, and forest and savanna in equatorial forest. After identifying those different fractions there, we came back to our model and realized that while they were predicting just for 2 poles, we had found 3. This is a occluded P on the top. Here is a non-occluded P. P means phosphorus here. And down here we have organic P. So we found that the non-occluded is really more than 50% of the total. So we were wondering, okay, what is this non-occluded P associated with? What's the dynamic behind here? And we started thinking that, okay, in our soil, we don't have a calcium. Calcium also controls P, but it's very poor in calcium. So the remaining is iron and aluminum. And we tested iron and aluminum. Total iron, we use the X-ray fluorescence, and aluminum, free aluminum, pedogenic aluminum, and iron, we use the citrate, CBD, and we use the ammonium oxalate. Okay, now, okay, we got that. How all of that plays together? What is the story? To better understand the dynamics that goes there, the phosphorus and the iron side, what's going on? And we came up with the idea, okay, we're gonna run structural equation modeling that will give us, it's a path analysis to see where everything started and where it ended. So it's a conceptual model, assuming a causative relationship. So we started with the precipitation and vegetation, how that is impacting your iron and aluminum, pH, and so organic carbon. And we brought the different fractions from Hadley extraction. And then we added to that in the system, Bray P. Bray is known, we consider that as a reference. So we imagine all kinds of connections between all of these variables. Once that was set, we ran everything in R. We ran multiple linear regressions, and the truth came straight out. We realized that precipitation and vegetation really has an impact on iron, and not any kind of iron, amorphous iron, more importantly. And amorphous iron has become, as you can see, the hub for all the phosphorus, your dynamics in the soil, in the very weathered soil like the one in Sankuru. We see a very strong correlation with the occluded P, raising PI, HCl, the sodium hydroxide, and bicarbonate hydroxide PI. That is controlled by iron ammonium, iron amorphous, I'm sorry. Yeah. And of course, going from what we had earlier with this many assumed relationship, and the system was able to eliminate all of that based on the significance of the correlation. And this is what left. To conclude this third chapter, the third part, in spite of the highly weathered, in Sankuru, yeah, phosphorus is not completely occluded form or organic. We still have a non-occluded P that appears to be predominantly associated with amorphous iron. Walker and Sayers model, did not predict the continuation of third pool non-occluded, but for us here, it's real. It is not predicted. It was not predicted by Walker, but it's real for us. And this was found also when the same study was done in Hawaii. So could be something typical for a tropical soil. And in the future, of course, we hope that the people will think and use a local available amendment to try really to extract much of that iron from amorphous iron, much of phosphorus from amorphous iron. So to terminate my talk, a couple sections here as a summary for pedogenesis. We found that the more diversified soil types on the forest and the savanna, we identified those, the candy udor, the aqueducts, quasi-cement, the spoiler soil, and the humid in humidapt in AF, in the equatorial forest. And we had a humidapt and the humus depth dominating in the south, in AM and AW. And the vegetation has been dynamic on a geological scale, but it's stable enough really to allow us to see what we have observed so far. And climate and vegetation interaction influence the pupil, phosphorus pools and the stocks. We hope that provide some light into what we have found in terms of pedogenesis here. The soil is very, very weathered. In terms of agriculture implications, soil fertility is a real challenge in Sankuru. All the soil fertility, all the parameters are pretty down. However, the existence of a large non-occluded pool of soil really may provide opportunities for increasing nutrient availability. Yeah, that's possible. And under savanna, vegetation provides a much better agricultural condition than forest relative to P availability. Other consideration may not be that favorable, but for P, probably, yeah. Increasing organic matter, of course, input is very, very critical in this case. And we hope that future consideration would be given strongly to see if biochar can come and play some role here. I would like very quickly acknowledge some funding sources. The University of Notre Dame in Chumbe, Nicolas Diomo, Rebecca Wallo, and the staff, along with the students at the university, recognize the effort contribution from Congolese farmers. The committee, my committee members, and the SWAC faculty, everybody, I hope I didn't forget anybody. If that happened, I feel so sorry, but many, many people did help me in this journey. The team, Jelinski Lab, yeah. I embrace all of you ladies and guys, as well as the faculty and the staff at the University of Minnesota Institute for Rock Magnetism. With that, I thank you.
Thank you, Al, so much. We have probably just a few minutes for questions. If anybody has them, you can add them to the chat. I'll moderate that, or you can go ahead and unmute and ask at this point. We probably have time for 3 questions or so. Okay, we've got a question here, Al, if you can hear me, from Holly.
Yeah.
So Holly says, you mentioned the Aeolian sands and the relationship between grain size and latitude. Her question is, do you have any information on the age of the sand parent material deposition and the influence on soil development and taxonomy?
That's a very good one. Unfortunately, I don't. That's one thing that we had in our plan starting this research, but because of the limited budget, we could not implement any test in that regard. It would have been exceptionally helpful, and it's still in my mind because I intended to pursue this, to refine and expand. So I definitely hope that there will be some means available to do it that will help really reset the whole sedimentation in that area. Thank
Great.
you.
Thanks, Holly. Oh yes, please unmute to ask a question.
Oh, hi, Al. I am Yuhei. I'm a PhD student from Dr. Marginon's lab. And I have a question about your potential. You said that there's a potential to release the phosphorus from the non-occluded P fractions that may be able to improve the nutrients of those soils. And do you have any like potential strategies that you're thinking about to actually be able to exploit those phosphorus from the non-occluded pools?
Yeah, that's really another good question that comes into my longer vision, because personally, I think we can try whatever we can with the local resources. So what can we do to mine that resource, that those phosphorus retain in the amorphous iron? What comes right away is a biochar that has to be experimented. I know literature is pretty split in that regard, 50-50 kind of, but with 50% of the chances, yeah, I think it's worth to give it a try. So that would be probably the third step in this long project, that will be looking at how can we initiate some local biochar production and do the testing and see how that can help boost the pH. Yeah, because and even at that level, we will have to run some regression and see if up to which level we can take a pH without losing too much. Because during these tests here, we have seen that at some level, when we run a pH against the resin P, we saw that as the pH increases at some level, already we lose 40% of that plant available P. So we need to be careful about that. But I would, to come to your question, I would like to really experiment biochar, because organic matter, that would be very important, but there is no cow or livestock activities there, and the people needed to be instructed how to build compost. So that also is another avenue, but it's gonna take time. And that's the two alternatives that I'm contemplating in my next few steps. Thank you.
Yeah, thank you so much for your answer. I'm really excited to see if those approaches may change the phosphorus cycling with the pH changes. So
yeah, exactly. Yeah, great.
Thank you, Yuhei. So we have maybe time for one very brief question. Otherwise, we're going to start moving to our closed session with the committee. So I'll give about 20 more seconds here of space if anybody has one last brief question. Okay, barring none, again, on behalf of the committee, I'd like to thank you all for being here to support Al and his seminar. If you have any words of encouragement or thanks for Al, feel free to throw them in the chat and he will see them before we move to the closed session. So thank you all, and we will